vehicle moves with the maximum velocity v1, the frictional force acts in downward direction. Let us resolve the frictional force into two components. F cos theta, horizontal component, and F sin theta, a component which is acting vertically downward. The outward force is the centrifugal force, and it will be given by m v1 square upon r. Now in equilibrium condition, we can equate the forces as the force m cos theta is balanced by two downward forces F sin theta plus mg, and centrifugal force m v1 square upon r is balanced by two forces acting in the left hand direction, n sin theta plus F cos theta. Now from these two equations, if we rearrange the terms, let us rearrange the equation 1 as, we'll keep this mg on left hand side. This will be equal to n cos theta minus F sin theta. And equation number 2 will be m v1 square upon r. This will be equal to n sin theta plus F cos theta. We also know that F is the frictional force, and the frictional force F is always equal to mu times the normal reaction, where mu is the coefficient of friction. If we write it as mu s, then it will be coefficient of static friction. If we represent F as mu s into n, then the equation will become as mg is equal to n cos theta minus mu s into sin theta, and m v1 square upon r, this will be equal to n sin theta plus mu s into n cos theta. In this particular equation, we have to write n sin theta. Yes. Now, if we compare these two equations, if we divide equation 2 by equation 1, then we will be able to get the expression as m v1 square upon r divided by mg. This will be equal to n sin theta plus mu s n cos theta upon n cos theta minus mu s n sin theta. So from this particular expression, we'll be able to cancel m from numerator and denominator of the left hand side. So the left hand side will become v1 square upon numerator's denominator will come to denominator, so it will be arch. This will be equal to, we can take n common from the numerator, so this becomes sin of theta plus mu s into cos theta upon, from here if we take n common, then this will be cos of theta minus mu s into sin of theta. So let us cancel n also from here. And so the relationship will become V1 square upon Rg, this is equal to sin theta plus mu s cos theta upon cos theta minus mu s into sin of theta. Well, theta is angle of banking. So from this particular expression, we'll be able to write the relation for velocity as V1 square is equal to sin theta plus mu s cos theta upon cos theta minus mu s sin theta into arch. So V1 will be equal to under root sin theta plus mu s cos theta upon cos theta minus mu s sin theta into arch, and it's root. So this expression gives us the maximum velocity with which the vehicle can move on a banked road, which has been banked with angle of banking theta. As we are able to get the maximum speed, we can also derive an expression for minimum speed. Excuse me. For minimum speed, the forces can be resolved as again mg acting vertically downward, n will be perpendicular to the rope, will resolve the normal reaction as n sin theta acting to the left and n cos theta acting vertically upward, which will be balanced by mg. Now if the speed is very less, so that if the vehicle skids in downward direction, the frictional force will be acting in upward direction. So this is Fs. As this frictional force will be able to resolve this frictional force into two components. This will be the horizontal component and this will be the vertical component. So vertical component will be Fs sin of theta and horizontal component will be Fs cos of theta. Along with this, let us consider V2 as the speed with which or velocity with which the vehicle is moving, which is minimum. There the centrifugal force will be mv2 square upon r. And so, if we are going to resolve these all forces, the forces which are acting in upward direction are n cos theta plus Fs sin of theta, and these two forces are balanced by mg, weight of the vehicle. The two forces acting on the right hand side, one of the forces mv2 square upon r plus Fs cos of theta, and this is balanced by n sin theta. So we can express the equation number 2 as mv2 square upon r. This will be equal to n sin of theta minus Fs cos of theta. And so, comparing the two equations now, I can write the equation as mv2 square upon r upon mg. This will be equal to n sin theta minus Fs cos of theta upon n cos of theta plus Fs sin of theta. We can express the frictional force as mu times the normal reaction. And so the equation can be expressed as mv2 square, let us take this r downward over here, so mrg, this will be equal to n sin theta minus n into mu s cos of theta upon n cos theta plus n into mu s sin of theta. So m will get cancelled from numerator and denominator on the left hand side, and so if we take n common, we can cancel it from numerator and denominator of the right hand side. And so from this expression, we will be able to write v2 square is equal to, in the bracket, sin theta minus mu s cos theta upon cos theta plus mu s sin theta. And so from this into r. So from this expression, we will be able to write the minimum speed with which the car can take a turn on band curved road is V2 is equal to under root sin theta minus mu s cos theta upon cos theta theta plus mu s sin theta, put a bracket, into Rg, and it's so here we are having two expressions. One expression is for V1, which is the maximum speed. V2 is the minimum speed with which the vehicle can take a turn on the curved banked road. Here you see the expression sin theta plus mu s cos theta in the numerator, cos theta minus mu s sin theta in the denominator. Here you will see sin theta minus mu s cos theta in the numerator, cos theta plus mu s sin theta in the denominator. But when on a curved banked road, if the vehicle moves with the velocity which is a safe velocity, it will be greater than V2, but it will be smaller than V1. It will be greater than V2 and it will be smaller than V1. Their vehicle will neither move, it will not skid in downward direction, nor it will move in the upward direction. It will move on the road without slipping either in upper direction or in lower direction. Then the frictional force Fs will be 0. If the frictional force is 0, then coefficient of friction will become 0. If the coefficient of friction becomes 0, either you use any of the expression over here, the expression is going to become as V is equal to under root sin theta minus 0 upon cos theta plus 0 multiplied by Rg and its root. So the expression becomes V is equal to root of Rg sin theta upon cos theta is going to become tan theta. So this is the expression for a vehicle moving on a banked curved road where the angle of banking is theta and V is the safe limit of the speed with which the vehicle can take a turn. Now in this particular expression, as we see, once the road is been constructed, radius of curvature is fixed, it is not going to change. For a given place, acceleration due to gravity is constant, and for the speed for which the vehicle is to be moving on the road, if it is been decided, then the angle of banking theta become a constant term. So for that particular constant angle of banking, tan theta value will be constant. So R into G into tan of theta, this value will be constant, whose root will also be a constant value. And so for a curved banked road, the safe limit is fixed, above which there is possibility of a car getting toppled down, move outside the curvature and meet an accident, or below that a car or a vehicle can skid in downward direction. So the safe limit of a velocity is given by V is equal to root of Rg tan of theta. So from this we are able to get two expressions for the curved